All right. So you thought I had forgotten about you, but that's not true. I've just been busy recording videos for my other course. Um, so we're going to go into a topic now, which is essential. This is one of the core ideas that governs how metals behave and how we're going to analyze them as we find them within some proteins and enzymes. And so what we need to do is related to what we've been talking about, right? So if you go back to the previous videos, we talked about the orbitals and how they overlap and how we make a bond and draw a molecular orbital diagram and all these kind of things. So what we're going to talk about here is crystal field theory. And really what we're going to be dealing with is ligand field theory. And so if you pop in either one of those terms into Google, you'll get a plethora of sources for it. But crystal field theory and ligand field theory are going to be used to help describe how the molecular orbital diagrams for our metal complexes look when they are within a protein. Okay, so let's try and visualize this for just a second. Okay, so let's say we have Mr. Generic Metal. Okay. And Mr. Generic Metal has 5 orbitals, right? We have our, let's do z squared and x squared minus y squared, xz, yz, and xy, okay? Now, if I take this metal and it's just floating out in space, then all 5 of those orbitals are degenerate, right? They're at the same energy level, okay? But as I start to bring a ligand closer to this metal, it's going to start to shift my orbitals. So here's Mr. Generic Metal, right? We'll give that M. What we'll do is I'll draw in a set of axes here, right? So there's my, we'll do Z going up. That's typically how it is, right? We'll do X and then we'll do Y back here, okay? And of course they extend in, you know, the three-dimensional space here, right? So if I bring a generic ligand in on my XY plane on axis, okay? If I bring a generic ligand set in on my XY plane on axis, it's going to start to interact with the orbitals that exist on the XY plane for the metals. Okay, so if you remember, just like what we did previous, whoops, let me switch colors here just to not get too confusing. Red seems decent, okay. So let's say I have an orbital that's sitting on my XY plane, right? For instance, my x squared minus y squared orbital, then whatever ligands are coming in to bind to that metal are going to bind to that x squared minus y squared orbital. And that's going to change the energy of my orbital here, okay? Because we're going to make a bonding and we're going to make an anti-bonding combination. Okay? Similarly, let me just try and erase this here for just a second. I guess it would have been easier for me just to draw a completely new thing, wouldn't it? But hey, what do you want, huh? Okay. Similarly, if I have a ligand that is coming in on my z-axis, then any orbital on my metal that lies directly on that z-axis can interact with it. For instance, right, we have our z-squared orbital. Okay, remember our z-squared orbital looks like a p orbital with a little donut around it. And that's going to cause my z-squared orbital to change in energy. Okay, so the idea is this, right? The idea is very similar to what we did in class and in the lecture and all that, right? When we're looking at how our ligands are going to get affected, right, we need to kind of sketch in our orbitals and we need to sketch in our ligands and see how they approach. Okay, now what I'm going to do here for just a second is I'm going to skip about, maybe a month of class. I wish I could teach you guys inorganic chemistry because we'd go through something called group theory, and group theory is basically a mathematical approach to looking at how things transform and how things shift in three-dimensional space, and we talk about point groups and space groups and all this other kind of stuff that's in there. So I'm going to skip this pretty heavily, okay? And so I'm going to start using some terms here in just a little bit, and it comes from this group theory idea, okay? So, but before that, so let's say we have an octahedral, okay? Let's say we have an octahedral metal, okay? A metal ligand complex, right? So if we have something like, oh, I don't know, iron, okay? Let's say we have iron hexachloride. So iron hexachloride, and let's give this a 3- charge. Okay. So as you can see, okay, we've got 6 chlorides surrounding this one iron. Okay. And these 6 chlorides are lying on the axis. Now, the reason why they're going to lie on axis is because that's where they're going to be able to make the most of our interactions, right? They're going to be able to interact with the x squared minus y squared and the dz squared orbitals, okay? These set of orbitals right here, okay? These set of orbitals right here lie on axis, and these set of orbitals here lie off axis, okay? The chlorides are going to come on axis to make the strongest interaction with the z squared and the x squared minus y squared orbitals, okay? So if you haven't already figured this out, or if it's not quite making sense yet, go pull up a picture of how the d orbitals look, okay? And I'll post some links for you guys online there, okay? Now, as we bring these two together, I'm going to just move this out of the way because I'm going to need some space here, okay? So I'll put that up there. Now, as we move together, we're going to break the degeneracy of these orbitals. The stuff that interacts, right? The stuff that interacts is going to go higher in energy, okay? So our x squared minus y squared and our z squared are going to go up here. And we're making the assumption that we're not going to interact anything here, right, off axis. So those will go lower in energy. Now we're making a couple assumptions here, right? We're making the assumption that we're bringing negative things together, right? And when you bring negative things together, the electrons on the iron and the electrons on the chlorines, right, they're going to repel, and let's push the yellow set of orbitals up, and if we're not doing that repulsion, then the blue can go down in energy, okay? So this is the essentials of crystal field theory, okay? It's basically a way of describing how ligands and metals are going to come together and what's going to happen to the orbitals themselves, okay? But this idea right here, right? You're going to see this splitting pattern quite a bit, right? This is how the generic octahedral d orbital set is going to look. Now there's a couple of important things I need to tell you here, okay? Our yellow ligand set here now has 2, okay? Our yellow ligand set has 2 orbitals that are of equal energy. These are now degenerate. We will call these Eg. Now, the E and the G comes from that ligand field theory that I was describing earlier. The E just stands for a 2, okay? So E is just 2, a doubly degenerate. So 2 degenerate orbitals. And the G, it comes from the German word for gerade, and that is, it means that they are symmetric with respect to inversion. Now, what in the world does that mean? Well, let me kind of briefly describe this for you guys. So here is, you know what? Let me keep this. No. Let me keep this as simple as I can. So let me draw my z squared orbital, okay? And I'm going to put a black dot right in the middle, okay? Now, the G just stands for they are symmetric with respect to inversion. So inversion means I take all of my mathematical points and draw them through the origin, okay? So what I mean is this. If I have a point, let's do it in green. So if I have a point here which represents a specific mathematical solution, to draw it, I'm going to draw it through the origin, right? And bring it down here. So if it's at x, y, and z, then down here it'll be at negative x, negative y, negative z, okay? So that's just what we mean by inversion. We're drawing it through the origin and just changing our positions, right? Okay, who cares, right? What does that matter? So it works like this, okay? If something is symmetric to inversion, it means that if I do an inversion operation on this, it's going to look the same. So if you can imagine looking at my z-squared orbital here, if you can imagine kind of pulling the orbs through the origin, like in pulling the donut, right, to the opposite sides there, right, it's going to look the same after I invert something. That's as opposed to a p orbital, right? So here's a p orbital. Here's my origin. If I do an inversion, right, so a little italicized I just means an inversion, then my p orbital will look like this. That is not symmetric with respect to inversion. Okay? I know. It takes a while, and like I said, we skipped about a month of class. We just don't have the time, and you know what? You guys don't need this either, right? I am going to be referring to the EG set quite a bit, and what I need you guys to know is that the EG set just means my x squared minus y squared, my z squared, okay? They are doubly degenerate. The stuff with respect to inversion is not that important. I'm just telling you where the letters come from. These letters are very important, okay? These are important. They do mean something. I'm just very, very, very briefly, and I'm skipping over a lot, right, just introducing what it is, okay? We go down here to our xz, yz, and our xy. These are known as our T2G set, okay, our T2G set. Now, some of this stuff you might already be able to figure out, okay? The T means that is, hang on just a second, let me pause here. Sorry about that, I had a little coughing fit there. Allergies are driving me nuts. But anyway, sorry, so the T just means it's triply degenerate. Whoops, can't spell. The 2 can mean a couple things. So let me describe it with respect to an octahedral set here, or this particular molecule. The 2 here means that it's symmetric, okay? With respect to WRT, with respect to a C2 axis that's perpendicular to the hello. Sorry about that. That's perpendicular to the principal axis of rotation. Principal axis of rotation. Wow. Man, I'll tell you what, look, group theory, when I was going through my graduate work, I mean, nothing makes you feel smarter than when you understand what group theory is. Because, man, like, what did you learn in class today? Well, I learned about, symmetric, perpendicular axes of rotation, blah, blah. Okay, anyway, who cares, right? It means something, and it's kind of the same idea as what we talked about there with the G, right? When we are looking at group theory, we're looking at translations and rotations and inversions and all these different symmetrical sets that explain how the orbitals and the subsequent ligands and all this kind of stuff, right, behave with respect to those mathematical translations, okay? So I don't need you guys to know this stuff, okay? What I need you guys to understand is that I'm going to be using this terminology EG and T2G. Really, the important parts are understand what the different E and the T and all that stuff stands for, right? That's going to be important. We're going to see that quite a bit. So whenever I refer to, hey, look at the EG set, you're thinking, okay, it's x squared minus y squared, right? And the z squared orbitals, and they're doubly degenerate. If I say the T2G, right, we're talking about our xz, our yz, and our xy set of orbitals, okay? And then here, the G means the same thing that it did up here, right? So we're talking about with respect to inversion, okay? Good. Still with me? All right. Let me clean up here. Well, actually, you know what? I'm going to take what I drew there. Let's see. I did blue and yellow, right? Okay, cool. So here are my orbitals. Right, here's my T2G set, and here's my EG set. So z squared, right, x squared minus y squared. And xz, yz, right, and xy, okay? Remember, we're dealing with energy, right? So the change in between these are called delta O or delta octahedral, okay? So when I talk about the energy, when I talk about the delta octahedral or the gap between the orbitals or the change in energy of the orbitals, I'm talking about this delta octahedral. Now what we're going to learn in just a little bit is that depending on what ligands, right, depending on what's bound to the metal, it's going to change that delta octahedral. It's going to either make it bigger or smaller, and that's going to change some things for the metal, okay? And so we're gonna come back and introduce this idea in just a little bit here now, okay? So if I'm talking about my d orbitals for an octahedral ligand, this is what I expect you guys to be able to do, right? Not too bad. Right, we got a T2G set, right? It's xz, yz, and xy, and my z squared and x squared minus y squared, okay? Now, we could go through and we could do the same set of analysis, right? The same idea for tetrahedral, okay? So let's do this for tetrahedral. So remember, we would start with a all-degenerate orbital set. And if we do tetrahedral, what's actually going to happen is this. Okay, so we're going to have an E and a T2 set. Okay, now these aren't EG and T2G because there is no inversion center in a tetrahedral geometry. So we can't have, right, if we don't have inversion centers, then we can't say something is EG or T2G, right? It's just E or T2, okay? The T still means it's triply degenerate. It still refers to the three orbitals, okay? And the E still refers to the z squared and the x squared minus y squared. Now, how in the world and why in the world does this shift here? Well, this is where it gets a little bit tricky, okay? So I'm going to post a link to you guys to kind of show the images for how it gets to this. Because, right, what it involves is if you have a metal, right, so there's our buddy metal that's in the middle, and an orbital, to assess the tetrahedral orbitals, you imagine your metal in a perfect cube, okay, and the ligands are, oops, I forgot to draw my cube, right, let me move this a little bit here. Right, so the metal is directly in the middle of this cube, and my ligands are on the four respective corners of the cube. Now you're like, how in the world is that tetrahedral? Well, trust me, it is, okay? And so from here, we could go through and we could do an assessment. We could start to draw orbitals in and see how they interact with specific sets of ligands and all this kind of stuff. Trust me, it works the same way as with octahedral. It's just tetrahedrals are a little bit more difficult to visualize. But I'll post some pictures for you guys about this stuff, okay? So anyway, here's kind of we'll wrap up this video here to give this a nice a nice stopping point before I move on to the next topic, right? But when I'm talking about the orbital splitting diagrams for octahedral and tetrahedral, right? This is what I need you guys to know. This is going to be key. I'm going to build upon this concept moving forward, right? For those of you guys who thought, oh, this is easy, I just need to memorize 2 things. Don't worry, it gets worse, okay? But here's kind of the brief, very, very, very brief introduction to crystal field theory, and we're going to expand upon this in the next set of lectures when we talk about ligand field theory and all this other kind of stuff, okay? All right, so see you guys in the next video.